Okay, multiple linear regression, or MLR, extends simple linear regression from chapter 7 to more than one input x. So if we write out the model, I have that my y's follow a linear relationship, but now I'm going to write xi1 for the first x, and then beta 2 xi2 for the second one, and I may have as many as d of them. And then I'll still have a random error, and that random error will still be IID Gaussian. Okay, so that's the setup. Just like in chapter 7, we can write this another way, actually two ways, but here's the first one. So I have the x's on the right-hand side of a conditioning bar for y, so that I can go directly into the Gaussian with a particular mean. And I like this because it lets me use a lot of the results about means from chapter 2. Right, so this whole thing here is like a mu I, where that mu I is calculated based on dx's and d slopes and an intercept. There's a third way that's really helpful. It's my favorite, but it involves upgrading sophistication to linear algebra. But linear algebra, once you understand it, simplifies a number of things. So let me write it, and then I'll talk about it. So this is an n-variate, multivariate normal distribution. We talked a little bit about bivariate normal distributions in chapter 7, so that would be n equals 2. But here I might have n equals 100 or something like that, number of data points, and my y is a draw from a multivariate normal with a mean that is a x matrix times a beta vector, which I'll explain in a moment, and the covariance is an identity matrix times sigma squared. So let's talk about these things. Y is an n vector. It has all of the observations. That doesn't look like a y, but it should. So it's a column vector, so I'm writing it out as a row and then transposing it. So it's an n vector. And beta is a p vector. Actually, a d plus 1 equals p vector. So it looks like this. So it's a p equals d plus 1 vector. And then in is an n by n identity matrix. And then x is an n by p. It's called a design matrix, or you could call it an input matrix. And its rows are xi's, again transposed so that I can write it out horizontally. It has a leading 1 to take care of the intercept. That's what gets multiplied by beta 0. And then the things that get multiplied by beta 1 up to beta d are xi1 up to xid. And if you look closely at this, SLR, or any of the three ways of writing it out, is a special case where d is equal to 1. When d is equal to 2, the linear surface isn't a line, it's a plane. When d is 3 or bigger, the linear surface is called a hyperplane. So we say hyperplane when d is equal to 2, you can just about visualize a plane going through some points because you can use perspective in 2 dimensions. But when d is 3 or bigger, you can't visualize this hyperplane, so you have to get a bit creative. Okay, I want to go to R just very briefly here to kind of keep our running example going, in particular to show you what the design matrix looks like. So fitting our first MLR, what we need is to create this design matrix. So capital X is going to be, we're going to continue on from our polynomial regression example from part B of this chapter 13 vignette. So I'm going to column bind a 1 vector with x1 and x2. Actually, it wasn't called x1, it was called x because we were doing a polynomial regression. So x1 is x and x2 is x squared, if you recall. So we already have a vector of y's, and now we have a matrix of x's that is n rows long and p equals 3 columns wide. And with that, we can do all the calculations that are necessary. And I'll come to those calculations in just a moment. So how do we interpret these things? So beta j, for j equals 1 up to d, is the change in the mean of y given all of the inputs for a unit change in xj. So holding all of the other variables constant, this slope beta j is the average change in y per unit change in xj. So that's how we interpret that. I know what you really want to know is, how do you estimate that? So calculating the MLE, which is our automatic way of estimating parameters, is the same as in chapter 7, where we wrote down the density of a Gaussian distribution, took its logarithm, and then took its derivatives to maximize. It's going to be just like that, but via a multivariate normal density with x times beta in for the mean, and the identity matrix times sigma squared in for the covariance. So if you look up multivariate normal on the internet or on Wikipedia, it'll be parameterized in terms of a mean vector mu and a covariance matrix sigma, and you would plug these values in to get the density. And if I express those as a function of the parameters involved in my multiple linear regression, I will get a density that looks kind of like this after a little bit of simplification. Okay, so that is the density with x beta for mu and 1 over sigma squared, basically, or sigma squared times the identity in that multivariate normal density. When I take the logarithm of that, the product turns into a sum, and some parts of it, like the 2 pi n root over 2, is constant with respect to the unknown parameters beta and sigma squared. So the parts that I need to do the calculus are here. Okay. And I really like to expand out. This is a quadratic, right? It's like an a minus b times c minus d, where the a where the C and the D are basically the same as the A and the B. So I can write this all out as C minus n over 2 log sigma squared minus 1 over 2 sigma squared. And I get a y transpose y. Sometimes we call this FOIL. I remember that from middle school, right? Maybe you didn't call it that in middle school. 2 y transpose x beta plus beta transpose x beta. There's two of these y transpose x betas. One of them is beta transpose x transpose y, but that's a scalar, and so is y transpose x beta. So there's two copies of the same thing. I'll leave that to you to look into. Okay, so I'm going to take the derivative of this log likelihood with respect to the vector of slopes and set that equal to 0 and solve. So when I take the derivative with respect to beta, the log sigma squared doesn't matter. The quadratic comes down and it becomes 2 times by the chain rule, the derivative of what's inside. So I'm going to get 1 over 2 sigma squared times 2, which is going to be sigma squared, and then x transpose y plus x transpose x beta. And when I move everything around, so one part of that sum is on the left of the equals and the other part of the sum is on the right. I think I'm missing a minus. I apologize for that. There's a minus right here because of the minus that's there. I'm going to get x transpose x beta equals x transpose y. And so beta hat, when I move to everything onto the right, is x transpose x inverse x transpose y. So that is the solution to my MLE. And if you squint closely at that, you'll notice that this looks like B1 from chapter 7. Remember, one of the formulas for that is SYX over SXX. Look at the SXX. That's like x transpose x inverse. Inverse is sort of like the matrix equivalent of a denominator or a reciprocal. So it's on the bottom, and then x times y, or SXY, is on the top. And in fact, if you do this in the case of d equals 1, you're going to get exactly the same value through the matrix formula on the left as you would with the simpler slope formula on the right. In fact, I left a number of things in chapter 7 for us to do here in chapter 13, and this is sort of the beginning of that. So let me wrap up this MLE calculation by going over into R and doing this formula, so solving for the MLE. So I need to calculate x transpose x. So the transpose function in R looks like this. Matrix multiplication looks a little funny. So that's how you multiply the transpose of a matrix by itself. And then if you want to invert it, I call this xtxi, the inverse of x transpose x. In R, you do that with the solve command because you're solving a linear system, in this case, with the identity. So that's how you invert in R. And then x transpose y, so that's going to be the transpose of x again, but this time times y. And then finally, I can calculate beta hat. So beta hat is x transpose x inverse times x transpose y. Okay, and we can compare that against what we calculated earlier, right? We did it with the LM command. So coif, we called that one lfit3. So, oh no, it was lfit2. Sorry about that. So let's do rbind, b hat, and lfit2. I was looking at the wrong place in my notes. Coif lfit2. what is LFIT2? Oh, isn't that what I calculated? Why can't I do an R bind of those two things? Coif LFIT2 and I don't know why I'm having a morning here. Could not find function. I'm just doing everything wrong. Number of columns. I think it's just complaining that this is a matrix. Let's see if I fix it there. Good. Okay, so they are the same thing, but it just took a little work to massage those into a way that we could see that what we calculated last time by the LM command and what we just calculated with the formula is exactly the same numbers. Okay, back to the whiteboard. This is a heavy whiteboard lecture. I want to tell you about an important projection result for multivariate normal random vectors. In fact, if you go to the Wikipedia page for the multivariate normal and search that page for the word projection, you will find this result, which says that if a random vector y is n-variate normal with some mean and some variance, and we're using x beta and the identity times sigma squared, and P is a P by N projection matrix of full rank, then P times Y is P variate normal with mean P times mu and covariance P sigma P transpose. Okay, so why am I telling you this? Consider the following projection, which is X transpose X inverse X transpose, so that we can write beta hat as a projection of Y. So look at this formula here. It's almost the same, except it's missing the Y, but then I put the Y on before calculating beta hat at the end. Now I can use this result, observe that P times X beta is X transpose X inverse X transpose X beta, which is equal to beta. And P times P transpose, thinking about the sigma as a scalar times the identity, is X transpose X inverse X transpose X, X transpose X inverse, so I'll get some cancellation, is X transpose X inverse, and therefore beta hat, which is a projection of Y, is P variate normal with a mean of beta, that's this guy coming in here, and a covariance of sigma squared times X transpose X inverse coming from there. So we found the sampling distribution, right? This is our MLE, and this is its sampling distribution. And we found it for all of the coefficients of beta, all the slopes and the intercept at once. Remember, I skipped some stuff when we did this in chapter 7, and we did them separately one at a time. But now I'm able with the linear algebra to do all P of them at once. Okay, so the last ingredient that I need before I can use this important result and show you what you get from it, I need to talk about what to use for sigma squared, right? Because we have a sigma squared in the sampling distribution, and we don't know it. And remember, if we can estimate it and find its distribution, and if it's an inverse chi-squared, then we can use a student t sampling distribution. So let's write out the likelihood again, but plug in the estimate of beta, so this is the log likelihood, and view it as a function of sigma squared. So I'm going to get minus n over 2, just copying from what we had earlier, minus 1 over 2 sigma squared, y minus x beta hat transpose y minus x beta hat. I'm going to take the derivative with respect to sigma squared and set that equal to 0. And I'm going to get minus n over 2 sigma squared. And then I'm going to get plus 1 over 2 sigma squared squared, which is sigma to the 4, and then times y minus x beta hat transpose y minus x beta hat. Now I just need to cancel the factor of sigma squared and move the negative 1 onto the other side and make it positive. And when I do that, I get an estimate of sigma squared that's 1 over n times this quadratic form. And you can show that just like in chapter 2 or in chapter 7, this is a biased estimate, but you can correct it. If you divide by a number smaller than n, that corrects for the degrees of freedom lost in estimating p beta parameters, d slopes and 1 intercept. So people prefer to use s squared, which is 1 over n minus p times y minus x beta hat transpose y minus x beta hat. So I'll draw a box around that one as our estimate. And you can show that sigma squared, the unknown parameter, has a distribution that is a scaled inverse chi-squared. So you can use student t for hypothesis testing and confidence intervals, which are calculated in the usual way. Those are estimate minus standard error estimate minus 1 to know divided by standard error for the test with a t distribution and n minus p degrees of freedom, or for confidence intervals, it's estimate plus or minus student t quantile times standard error in the usual way. So the way that I'm going to wrap this up here for this example is that I'm going to calculate standard errors and compare to what we get from the summary command on the LM object. So P is the number of columns of X. Remember, X has 2 columns for the 2 inputs and 1 column for the intercept. And N is the number of rows of X. And my estimate of S squared is going to be the sum of Y minus X times beta hat and I could write that as a vector and its transpose in a dot product, or I could just sum those squares because they're the same on both sides of the dot product, divided by n minus p. Okay, so there's my estimate, and I can compare that to what we get from the summary command for L_fit2, but I gotta get the sigma. It gives me sigma and I gotta square it, so that should be exactly the same number. and it is. And then we'll complete the summary table. What do I mean by that? When I do summary LFIT2 coefficients, I get a table, and we've looked at that table before. So now I can look and try to get those standard errors. So the standard errors are going to be the square root of the diagonal of this, of s squared, sorry, times the diagonal of x transpose x inverse. So let's take a look at those. 1.15 and then 6.74 times 10 to the minus 3 and 8.72 times 10 to the minus 5. So that gets me the standard error column. My t-statistic for doing the hypothesis test is going to be the estimate minus the want to know, but the table is using the want to know of 0. If you want a different value, then you have to put a different number in here. So if I write want to know is 0, then I put want to know here, but if you want to, you could put a different value other than 0, and then I divide by the standard error. Okay, and I print what those are. Those are the t-values. I call them t-stats, but R is calling them t-val, so minus 41, and then 30, and then minus 16. And then to calculate the p-value, I'm going to take 2 times a density from the t minus absolute value of t, and n minus p degrees of freedom. And you can see that that should match the last column. Well, now you can't see it. I better print the summary again. So there we go. 2.2 times 10 to the minus 89. So we'd reject the null hypothesis that the intercept is 0. And we definitely would reject the null hypothesis that the first slope is 0. And we would definitely reject the null hypothesis that the second slope is 0. I'm going to leave confidence intervals to you. It's just the inverse of that same calculation. And wrap up by saying something about prediction. So prediction for a multiple linear regression involves another projection. Since my fitted values, which I get by taking the original inputs and multiplying them by beta hat, notice how that's an upgrade of the fitted values from chapter 7, is a projection of the original y's where the projection is x times x transpose x inverse times x transpose. And sometimes this is called the hat matrix, which is why we use the letter H, because it puts the hat on Y. So if I take the hat matrix and multiply it by Y, it'll give me Y hat. Kind of a cheeky statistics mnemonic. The details of this, of how to use this, oops, I wrote hot, of how to use the hat matrix for prediction at new xp are provided in the book. This was already getting kind of long, but it basically involves working with that hat matrix at new locations. So check that out.